This is our lecture 8, and if you look at the parts on the computer, this is a part of the fourth part of lecture series. This fourth part was devoted to different technologies that are used in local area networks, actually wired local area networks, because we will have one more lecture on wireless local area networks a little bit later. This particular lecture series, now we had like lecture 6, which was logical link control, 802.2, and then lecture 7 was about Ethernet and other legacy LANs, which was 802.3, 802.4, and 802.5. And in that lecture series, we came to the point that Ethernet is the one that has survived, and then we compared Ethernet with the others. We discussed a little bit about why Ethernet survived, and bottom line is that it survived and we don't know why. Maybe in a good marketing environment, maybe better, in a better window of time, whatever, I don't know. But basically, Ethernet was the simplest among the alls, okay? And then we said that all the other, in fact, activities which has been done more recently in the past few years, Ethernet was competing with 802.5 up to like late 1990s, up to like 1995, 6, 7. But today, certainly Ethernet is the dominant one. And then in the past like 3-4 years, a bunch of like subcommittees on Ethernet have been formed, and these subcommittees were doing different things. And the subject that we will discuss in lecture 8 is related to those subcommittees. Okay, so that's what we are going to do. Among these subcommittees, what has happened and the detail of those subcommittees. In order to see that, I come to the lecture now, and I start this lecture, which I call it Fast Ethernet and Beyond. The reason that I call it Fast Ethernet and Beyond is that Fast Ethernet is 100 megabit per second. Today is the most popular in the offices, and beyond that are those little things, subcommittees, which happened right after. Okay. Part of those subcommittees are working on the MAC layer to increase like flexibility of Ethernet, which are VLAN and full duplex operation. Then part of the others are working on higher speed, and also with Ethernet 100 megabit per second in a smaller number of wires, also integration of voice into Ethernet. Okay, these are the complete activities that are related to Ethernet, and we will discuss. So basically, for the fast LANs in general, we have a bunch of 100 base. 100 bases are the ones which are like 802.3 variety of versions. Okay, there are several versions of 100 megabit per second baseband and baseband Ethernet type. Okay, that's one. Then there is a standard. All of those 100 bases are under 802.3. Okay. Then there is another one which is called ISO Ethernet, which is isocronous Ethernet, which is taking the Ethernet and use it as a PBX, add voice to Ethernet. That one, since the MAC layer is different, it's discussed in 802.9. It had a big hype in late 1990s, but didn't expect the market predictions. Okay. Then more recently, in the past like 2-3 years, they started to go to gigabit Ethernet. First, they went to 1000 base T and X, which are 802.3Z and AB. Okay, these are the ones which are 1 gigabit per second Ethernet for the backbone. Okay, and then more recently, as of this year, they went to 10 gigabit per second Ethernet. Okay, these are the ones that I call fast LANs, which are related to Ethernet. Then in addition to that, they had 3 other activities. One was FTDI, which was standardized by ANSI. If you remember, ANSI was American National Standard Institute. Usually 802 goes to ANSI, but this standard was made by ANSI. And then is 100 VGNE LAN, or DPAM. This one originally started with 100 base type of activities, but they ended up to a different MAC layer, so they shifted them to 802.12. Okay. Then there is another activity which is the so-called ATM lane. If you remember, ATM forum is working on ATM switches all the time. Okay. Now, what happens is that in mid-1990s, around 1995-6, when everybody thought that ATM is going to take over, they thought that, okay, now, what is the replacement for LANs? And then they said that's ATM LAN. ATM LAN emulator, which is lane. Okay, so I will discuss those 3 in another lecture. Okay, but this lecture is related to Ethernet-related fast LAN, which are the successful fast LANs. The other one are technologies that have always been also been discovered, just as a comparison. Okay. So to do that, if you remember this chart, we had this chart as a part of a bigger chart earlier, which is the history of Ethernet, how Ethernet evolved, started, and then went from thick cable to thin cable, and then to twisted pair. That's bottom line of everything that they did. But in between, they tried to sometimes add like fiber-based Ethernets, which are going to longer distances. Okay, and that's all of these standards that is starting from around 1983 up to 1993. For 10 years, they evolved. And these are all around the so-called legacy Ethernet. Okay, the last one was 802.3J, which is 10 base F, 10 megabit per second on fiber. Okay, so as the time passes by, they go from A, B, C, D, they go to new things. So by that number that you see at the end of the standard, you can look at the versions. Okay, what will happen is that when they go to a new version, they add some clauses. So one statement would be like 802.3J, for example. And then the other clauses are before. Original was, I don't know, something like, I believe, 20, 21 clauses, original Ethernet. And then they gradually added these other clauses, if you want to call it. So sometimes in the literature, people refer to clauses. Okay, but basically that's one statement that comes from it. Okay. Then fast Ethernet and beyond, which are the things that we want to cover in this lecture. According to the numbers, these are the numbers, like 802.3U, which defines 100 base T. That's the so-called fast Ethernet. Okay, this is most of the part of my lecture today is devoted to this, how they came to 10 megabit per second. Remember that they have just laid these wires, which are like 100 meters, twisted pair by now. And they are running 10 megabit per second on top of that. Okay. Now, what is next? Always they go like 100 megabit per second. Then the issue is that you want to design 100 megabit per second, which works with the previous one as well. Okay. So how do you want to devise that standard, really? Okay. Then after that, they started to talk about in 1997 about 3X, which is full duplex operation. Ethernet is half duplex. I mean, people use it either from both directions. Okay. they started to make some adjustment to have full duplex operation. We will discuss that. In order to do that, you need certain packets, and they have defined those packets at the MAC layer. Then, in 1997, also they had 3Y, which was 100 base T2. Means that the 100 base T that I have in here works on 4 pair of Cat3 and 2 pairs of Cat5. By now you know what is Cat3, what is Cat5. Cat3 is lower grade for telephone, Cat5 is office grade. And then they have Cat5e. Okay, we remember that from lecture number 3 or something like that. Now, 100 base T2 uses 2 pair of Cat3, which is lower grades, but more sophisticated modem technology to achieve 100 megabit per second. Okay, that one did not become popular. But the modem design technology that they used in there got extended to gigabit Ethernet later on. So we go over that, we talk about it a little bit. Okay. Now, then 88, they went to the gigabit Ethernet. Then also another thing which happens was 802.3 AC, which went for VLAN, virtual LAN. Also we will discuss that in this lecture. Then they went to 100 base T. Originally it was 100 base X, which was over fiber and shielded twisted pair. 1000 base T is working also on other mediums. Okay, like unshielded twisted pair. Then after that, as of last year, they started to go to AE, which is 10 gigabit per second. Okay, so the trend is that this standard tries now to go and capture the backbone, because gigabit and 10 gigabit per second are not the data rates that you need for the user. So now Ethernet wants to go and capture other people's, in fact, territory. Okay. So this is the whole story, and we go over this entire story in this lecture, which is lecture 8. So outline of this lecture, the way that I go over these parts is, first I talk about fast Ethernet, which is that 100 megabit per second. Then I talk about VLAN, full duplex, and pulse frame. Then I talk about ISO Ethernet. I talk about 100 base T2 and gigabit Ethernet. These are, hopefully I will finish them in this lecture and the lecture after now. But the whole trend in here is like you have the Ethernet, which uses this simple packet. Okay, this is the simple packet that I repeat several times because it's good to remember this thing, huh? Because it's very popular these days. Okay, it has a preamble, it has a starting delimiter, destination address, source address. It has 2 choices, but we always use the 6 byte. Okay, length of the data field, which is 2 byte, data itself, pad, and checksum. Checksum was what, 32 bits, which was the remainder of dividing all of these numbers from here to here by what? By a prime 33-bit number. Okay, so that was what it is. This is the checksum, and this is the format. Now, when we go to the places that they want to change, as I have said it before, change the MAC format and add more frames other than single frame, they come to where? They come to this length of data field. They come in here and they make some changes. Because this 2 byte that you have in here, you can represent more than 1500. Okay, much more than that. So you can put numbers which are not the address and then do other things. 2 of those other things that they do, one is the VLAN, one is what? Pulse frame, which is used for full duplex operation. And we will discuss that in this lecture. I mean in this lecture or in lecture 8. This lecture series, if you want to call it. Okay. So this is the frame format that we want to remember. Then basically another thing is that we want to remember that when they want to put these things together, already they have like 10 megabit per second installations. Now they want to put 100 megabit on top of that. So everything should be what? Backward compatible. So that's one of the challenges of these standards. The next one is now, just to remind you, we had like issues about like medium. We had issues related to modulation technique and also issues related to networking. In here, networking is really, in local area networking is only MAC layer for us. And the MAC, we have only to remember the packet length. Now, for the medium now, I mean, we had the cable, we had the fiber, we had the twisted pair. But the most important one is the twisted pair, really, because it's the most popular for distribution. Okay. Now, just to remind you, I have added some issues in here to talk about the characteristics of twisted pair. Okay. Number one is attenuation. Means that if you put the signal at one end and you look at the other end, which is that end of that 100 meter, okay, and you change your frequencies from 0 up to 100 megahertz, how does it change? This is one graph, okay, which shows that. So you have like, when you come to 100 megabit per second, you have attenuations in the order of like 23 dB, while at 0 or around DC, you have only just 2-3 dB attenuation. What is the impact of this attenuation that you have in here? This will change the waveform, shape of the waveform. It's like a filter. So you send like a square wave, but you receive a shape which is not a square wave anymore. Okay, in time. Okay, and when it's not a square wave anymore, you are going to make errors. Okay, detail of that we discussed perhaps when we were talking about transmission techniques. Another issue which comes to the picture for twisted pair is the issue of crosstalk, because these twisted pairs come in the bundles. Okay, so they have a variety of crosstalk. One of them was next, near-end crosstalk. You remember we talked about that before. I find these figures which are better from a website from University of New Hampshire. I have put it as a reference in here. They have very good actually explanation of the physical layer to describe gigabit Ethernet. So I got a few extra one I added today. One of them is this. It's very nice representation of what of next. Next, you have this bundle of 4 pairs. Remember that when you go to the 100 megabit per second, if you want to use Cat3, they increase the number of wires. Now these wires, they are going to interfere with one another. Okay, this interference at this end, from one to another one, this is called what? Next. These are measured next at different frequencies. Okay, attenuation in here. Okay, this is the loss at different frequencies. As I increase the frequency, it is going to be increased. So if I come, for example, to something like 100 megahertz, interference from one of them to another one is like 30 dB. 30 dB is 1,000 times. Okay? But if I come to 0 frequency, it's like 80 dB. 80 dB is a very, very small number. Okay? dB goes like each of them goes, each 10 dB goes for one more 0. Okay? So this is 10 times, this is 100 times, this is 1,000, 10,000, 100,000. So it goes several zeros less, like 5 zeros less interference, if you want to call it in that sense. Okay? But this is the next between these things if you take different type of couplings. I mean, you take A to B to A, C to A, D to A. This is what they have in there. Okay, up to 100 megahertz. There is another one, they call it FEXT, that we didn't discuss it before. FEXT is far-end crosstalk. Means crosstalk of this end to the other end. Okay, now this one comes because you have some leakage when you put the plug in. Okay, and out of that leakage comes to the other end. Okay. Now, these are like measurements of the what? Measurement of the FEXT. Measurement of the FEXT. FEXT, for example, when you come to 100 megahertz, which is the maximum of it, is around like 50 dB, which is 100 times what? Less than next. Now, why do we discuss that? Because when they want to go from one category of the wire to another category of the wire, they cannot change that attenuation. What they try to do, they try to adjust the FEXT and next. Okay? That's what they try to adjust. So protection of the wires against one another. Okay, that's what they do for that. Now, on the other hand, when you want to just get like a length of the channel, these FEXT and next are like noise, or like background noise that you have. Attenuation of the signal is what? Is your signal level, signal strength. The ratio of the signal strength to the background noise is related to the error rate. Error rate that they want for example, gigabit Ethernet is 10 to the 10, 10 to the minus 10. Means from every 10 to the power of 10 bits, only one error. Okay. To maintain that, however, you need certain level of signal to noise ratio. Okay. The good part is that as we discussed when I was talking about transmission techniques are really on and off. Means that within 1 dB, 2 dB difference, you go from 1 out of 100 error to 1 out of trillion error. Okay? Because error rate has the behavior of a waterfall curve. Do you remember I talked about waterfall curves? And so it goes like this. See, if you have like, if this is your signal to noise ratio, and this is your error rate. Error rate always you put it in exponential manner. Okay, so in here is like 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, comes down, 10 to the minus 4, 10 to the minus 5. This always goes like this. This signal to noise ratio is often in dB. Within a couple of dB changes, suddenly you come from here, which is 10 to the minus 1, which is real bad. Okay, the worst that you can get is what? 1/2. That's the worst error rate. Means that there is no control, huh? Because you send the bits at the other end, you have probability of error of 1/2. Okay, that's the worst case. Okay, the best case, but the difference between worst cases and the best cases is only a few dB. So those who are doing modem design, always they are fighting for 1 or 2 dB gain. 1 dB, 2 dB, 3 dB, especially on the wire. Okay, is a lot. When you go to the radio, that 1, 2, 3 dB is also important, because 1, 2, 3 dB means that you can change your transmission power. Means the life of the battery. Okay, each 3 dB is 2 times. If I save in signal to noise ratio, if I shift this curve, 3 dB less. Okay, if it is in radio, means that what? Means I can double the life of my battery, if you want to say. Okay, if I am on the wire, I can add 1 more bit per my symbol. Okay, So always people try. But anyways, the behavior is what? At certain signal to noise ratio, you're dead. Okay? And a little bit after that, you're alive. So it's on-off, in a sense. Okay? But anyways, now how do they calculate this on-off and relate it to FEXT and next? Okay? FEXT and next are going to be like this. See, as I'm increasing the frequency in here, this figure is coming from a different paper, so it's different. In the other ones, I was giving loss. In here, I have the gain. So if you look at the gain, actually, as you increase the frequency, the gain goes down from a little bit more than 0 to up to so much. Okay? And then these are your next, for example. These are your noise. This is your noise level at different frequencies. This is your signal level at different frequencies. Difference between these two is what? Your signal to noise ratio. Okay? But since it's different at different frequencies, you have to get a sort of average or something like that. Okay? Or you can take it at the data rate that you have. For example, if you have at 16 megabit per second for token ring, you come in here at 16, look at the level of the signal to the noise. Okay? But anyway, this picture shows you that as you're increasing your bandwidth, the signal to noise ratio changes. So in addition to the fact that the shape of the pulse changes, level of the signal to the noise changes as you increase. So you have to do something with it. Okay? And then you come up with these numbers. Okay? Numbers for the bandwidth. So you come with the tables. For example, you say that I have a table that we saw previously, I think, in our earlier lectures, that was saying that if I have a twisted pair, it has like 16 megahertz bandwidth, Cat3. Cat5 has 100 megahertz bandwidth. Do you remember that? And then we had Cat6 is like 200 megabit per second. Cat7 is like 600 megahertz bandwidth. We had a table on that. How did they made up that table? They come to this type of thing. Okay? For that. Okay. Now, what they have changed in Cat5 and Cat3 and Cat6 and 7, those are next and what? Next and FEXT. Okay. That interference amount, they have reduced it. They have controlled it more. Anyways, this is summary of those. I had this one again in a big table before. This time I have it in a smaller table. It has Cat3, Cat5, Cat5e, which are the important ones really for us. Cat6 and Cat7. Cat6 is 200 megahertz, which is not that important. Cat7 is like 600, which is a major change. People are interested in that. But the ones which are used today are Cat3 and Cat5. And Cat5e is a better version of Cat5. Okay. So, originally we had Cat3, then we came for Office, which was Cat5. Now people are working at Cat5e for gigabit Ethernet, actually. Okay. Which is a little bit better in terms of next and FEXT performance. Okay. So that's more or less review of everything that we had so far. Now we come to the main issue. When we are talking about like going to higher data rates, what are the means of going to higher data rates? We discussed that again in previous lectures. Okay, but in here I will review that. The way that I review it, I have just put the things, the tricks that people have played in Ethernet, okay, to go to higher data rates. Okay, so they have a number of standards, okay, a number of high-speed standards, which are more than 10 megabit per second. Each of them is playing 1 or 2 or 3, 4 tricks. Okay, what are those tricks? I have categorized it in here. Number one is that if you have like Cat3, performance is bad, increase the number of wires. That's one, the most common. Okay. The second one was what? Multi-level transmission. You remember that we discussed that. That rather than having 1 and minus 1, for example, I have 1, minus 1, and 0, plus 2, minus 2. I have 5 PAM. Okay. Next trick was what? If I go to multiple levels, what will happen? Do you remember? If I go to multiple levels, I'm going to send more bits per symbol. The signal-to-noise ratio stuff, the wire itself, and the way that it is treated, it gives you the baud rate, really. Okay? It gives you the baud rate, means symbol transmission rate. If you have symbol transmission rate, now you get tricky. You can send what? More number of bits per symbol. That's what we call it what? Multi-level transmission. Okay. Then there is another trick that they were playing, if you remember. That is multidimensional. Multidimensional means that I have 2 wires and the other 2 wires. I don't send the symbols independent. I send part of a symbol in upper wire, part of them in the lower wire. If I do a thing like that, I will gain something like 1 dB around that. Okay? If you correlate them together. But when I correlate them together, I have to correlate the detection at the other end and transmission at the other end. You follow me? So if I have one stream of independent in one wire, a stream of independent in the other one, I have 2 one-dimensional. If I make it 2-dimensional, I correlate the points in the upper wires with the points in the lower wires. That way I bring my error rates lower. Means that my required signal-to-noise ratio becomes what? Lower. And I'm fighting for that all the time. Okay? Now, in here, multi-dimension can be 2-dimension. Up to now we were talking about 2-dimension. But in gigabit Ethernet, actually, they use 4-dimension. They have 4 wires, so they have a 4-dimensional space. Okay? Out of that, they will gain something around dB, order of a dB. But that's very important, because that order of dB can bring you from like 10 to the minus 3-4 to 10 to the minus 10. Okay? It can increase very, very rapidly. Okay? Improve the performance very rapidly. Then, what else do they use? They use more efficient line coding. You remember we discussed that also before, that the most popular line coding that we were using so far was what? Manchester coding. Manchester coding is 1B, 2B. Each bit is translated to 2 bits. Okay? So efficiency is 50%. They try to play tricks, other codings, which are more efficient. Other line coding, if you want to call it, which is more efficient than Manchester. Another one that they use, they go to a stronger channel coding techniques. What was the channel coding techniques that you had so far? Was just this, the CRC codes. Is that right? You only had CRC codes for what? Which was used for MAC layer, actually. Okay? But these people at the transmission level, for the physical layer, they use coding. And then they go to a stronger codes. CRC were what? Block codes. What was a stronger codes that they had? Were convolutional codes and trellis code modulation. Huh? They try to use that. Actually, they use that in what? In gigabit Ethernet. Okay? A stronger codes. Now, with a stronger codes, with like, for example, trellis code modulation, you can gain up to 3 dB. It's very good. It's a lot of gain. Okay. Then they use equalizers. What are equalizers? Do you remember that if I put my waveform in here, like I send on a square wave, it gets distorted at the other end? Equalizer is something that it brings it back, reverses the effect of the channel. And they can do that adaptively. That's a very known technology. That's another trick that they play. They do that again in gigabit Ethernet. All of these top ones are in there. And the last but not least is they use scramblers. Scramblers, we talked about that before. are scrambling the data. In a sense, when you have continuous streams, they scramble it, you have more transition. That one, in a sense, also helps in the signal-to-noise ratio. Because a little bit of your errors is coming from timing error. Okay? If you have scramblers, your timing error becomes lower. Okay? When you go for very high speeds, they put that in there too. Okay? So you reduce the jitter, actually. Jitter in sampling your received signal. Okay? These are the tricks that they are playing. Now, what I will try to go over is first to start to talk about like 100 megabit per second Ethernet, which we call it fast Ethernet. And we will unravel that which tricks they are playing in there. And then later on we go to the other things. But most of the tricks are in the 100, actually. They're embedded in the 100. So this is the 100 base T, or generally the so-called fast Ethernet. This one, the technology had, like, if you want, two branches. One branch is 100 base T4. This is 100 megabit per second using 4 twisted pair wires. Okay. Then they have 100 base X. X has two parts. One of them is 100 base TX, which is uses twisted pair, which is using twisted pair, and there is 100 base FX, which uses fiber. These guys, any version of those, if it is fiber, it uses 2 optical fiber. If it is TX, either it uses 2 shielded twisted pair or 2 Cat5 twisted pair. Okay. Remember that these are upgraded. Means that T4 is designed for Cat3. But if it is designed for Cat3, it works for anything better, which is Cat5 or anything else. Okay. But this thing cannot work on Cat3. Okay. Not at all. Okay. So now these are the basic standards. Now, 100 base T4 is something new. Is a new transmission technique that they developed. 100 base X actually uses the physical layer of FTDI. FTDI, if you remember, was designed in mid to late 1980s as the first high-speed fiber backbone. And then later on they find the wired version of that. Okay. Now, it has 2 physical layers, one for fiber and one for twisted pair. Okay. But the twisted pair in there is Cat5 or shielded twisted pair. Exactly the same thing is happening in here. Okay. Cat5, if you remember, the bandwidth was how much? Around 100 megahertz. Cat3 bandwidth was what? Around 16 megahertz. If you play games with them, you can stretch this 16 to up to 25 megahertz, for example. For 25 megahertz of bandwidth, then you can go 25 megabaud. I mean, mega symbol, if you want to call it. Because baud, we use it for a different wording in computer science too. This other guy has a bandwidth of 100 megahertz. Okay, if you play a little bit trick with that, okay, you can stretch it to 125. And that's what they do, actually. So really, when they come to 100 base T4, they have like wires which are running at 25 and wires that they are running at 125. When they are running at 125 baud rate, okay, they are having only 2 pairs. If they are running on the 25 baud, they have 3 pairs actually. Now what is the trick? See, if I have 25 megabit per second times 3 is 75. So I have to play another trick to make it what? Make it 100. Okay. The trick that they play, they go to 3-level modulation. The other one is in here. You have 100 megabit per second bandwidth, if you want to call, to increase it and go to like 125 that they need for the type of coding that they have. Again, they go to multi-level, to 3 levels. If you remember, for 3 level, if you go for that equation that I gave you, which was probability of the symbol times log 2 of inverse of the probability, either you have equal probability for the 3 points, or you have like 1, 3, 1, 3, 1, 3, or you have the middle one 1/2, the other 2 are 1/4. Do you remember that? Either way, if you calculate that bits, it goes like 1.5 really, around 1.5. One is 1.5, the other one is 1.8. Means that if you go from 2 level to 3 level, your bandwidth increases around what, 1.5. Bandwidth of Cat3 for 100 meter was how much? Around 16. Times 1.5 goes how much? Goes 24. Okay? Which is, what do I want? 25. Close enough. Okay? Now, the other one is for the Cat2. For Cat5. For the Cat5, the bandwidth was how much? 100. If I go to tri-level, I can go up to what? 150. But I don't need more than 125. Do you follow me? Just going from 2 level to 3 level, okay, if I get that equations that we exercised earlier, I increase my bandwidth, okay? And they go for that in here to increase their bandwidth. Okay, now, that's one trick. So, I'm using, whenever I am in here, in TX, 100 base TX, or 100 base T4. For both of them, I have tri-levels for transmission. Okay, I'm using ternary, 3 levels rather than 2 levels. How about optical? In optics, I don't have multiple levels. Either it's on or off. So I have to do a trick really in here. I have to have one standard for the optics, which has what? It's binary. And I have to have something for Cat5, which is what? Which is 3 level. The solution that they have found in here is the solution that FDDI has used. If I go to fiber optics, the bandwidth is much beyond 100. Okay, so you go where you want. Okay, so what they do is that if you want 100 megabit per second, okay, they first do one layer of coding, baseband coding. Okay, that level, after they did that coding, they send the signal on the fiber. But if the medium is not fiber and it's like twisted pair, they have another layer of coding. So in here I have 2 layers of codings. One is the one that is common between both of them, and there is another one which is only for TX. The TX one changes the binary to what? Ternary. Okay. When you come to 100 base T4, what they do is they directly get the binary input, turn it to ternary coding. Okay? And these are the detail of the tricks that they play. And now I will go over those in a little bit more detail. Now, what are those coding techniques? For TX and FX, TX, FX are what? Cat5, the wide bandwidths. These are the ones which have symbol rates which are very high, and there are only 2 pairs of wires. Okay? Now, what they do is that they use a coding called 4B, 5B. I had talked about that before. Manchester coding was what? 1B, 2B. This is 4B, 5B. Means you have 4 incoming bits. You code them in 5 bits. Okay? But when you code them, you try to code them to secure at least 2 transitions in 5 bits. Why do you want transitions? You remember that for synchronization. Okay. Now, so that's the first thing. Okay. And what is the line coding technique that they use? After they got the 4 to 5 bit, they use NRZI, which we are familiar with. Was part of your exam, actually. So you get 4 to 5, and you do that. And then, if you did this 4B5 decoding, and you want to go to fiber, you just make it intensity modulation. Means that 0 goes for what? For no light. 1 goes for light. Okay. If it is cable, you do another layer of coding that they call it ML3 coding. MLT-3. How does that one work? This is a 3-level coding. Okay. Now, I can talk about that a little bit, like in the next line. But how about T4? T4, you remember now you have 4 pair of wires. For those 4 pair of wires, there is no replacement between it's only for wire, okay, not for fiber. What they do, they use a coding which is called 8B6T. T means 6 ternary, 6 3 levels. 8 bits are coming in, 6 3 levels go out. Okay? So that's what they do. Okay. Let me just go down first to what? To TX and FX, which are over 2 pair of wires. This is 4B5B coding itself. 4B5B coding, what it does, it takes 4 bits, codes it in what? 5 bits. But the way that they code the 4-bit to 5-bit, they do it so that at least they secure 2 transitions in here. If you have non-return to 0i, if you want to secure 2 transmission, what should you have in the coded waveform? You need to have 2 ones, because 2 ones guarantees 2 transitions. So this is what I have. 2 in here, 2 in here, this here 3, this is 4, no problem. But minimum number of ones that I have in all my codes are what? These are my entire codes. Minimum transition is how many? Minimum number of ones is 2. Okay? So my bits, which are coming 4 bits, I'm encoding them to 5 bits. When I go encode 2 bits to 4 bits to 5 bits, 4 bits is how many? 16 combination. 5 bits is how many? 32 combination. So out of that 32 combination, I pick up 16, which have at least 2 transitions. And then I have 16 more, which is left over. Nobody is using them. Those 16, I can use it for control signaling, actually. Remember that. I don't have much of control signaling in Ethernet. So I can implement it at the physical layer rather than in the MAC layer. Okay? That's the trick that they are playing in here. So they have like signals like idle, for example. Okay? Idle is all ones. A start of the stream delimiter, part 1, this is this, 11000. A start of the stream delimiter, part 2. End of a stream delimiter, end of a stream delimiter, part 2. Transmission error, and then you have a few which are invalid now. Whenever you detect them, that's error. So at a physical layer, you're taking advantage of some protection from leftovers, and you have some signaling, and then you have your codes. And your codes are so that they are securing what? 2 transitions per each symbol, 5-bit symbol. Okay? So this is the so-called 4B5B coding. Now it's very popular because it's used in what? 100 base TX and FX. Also it is used in what? FTDI. Originally it was designed for FTDI. Okay. Then, okay, now the data stream comes to the T. X standard. X standard has two formats. One is fiber. One is what? One is shielded twisted pair or Cat5 twisted pair, good twisted pairs. Now, the data rate which is coming in is how much? 100 megabit per second. Is that right? Then they add 1 bit to that. Because 4 goes to 5 bits. Becomes how much? 125. Is that right? So the transmission rate, the bandwidth that I need on the medium is 125 megabit per second. 125 megabaud, if you want to call it. Okay. If I go to fiber, no problem. 125 is available, so I go with the same coding. But if I want to go to wires, since the wire bandwidth is 100, I take this 125 bit per second stream, I translate it to what? Trinary. 3 level. Okay. What is the rule of going from 2 to 3? That's the one that you have in here. It's called ML-3 encoding. Again, ML-3 coding is used for what? Used for only wire, not for the fiber. FDDI as well as 100 base X. Okay, so actually 100 base X is FDDI Ethernet, if you want to call it. Because Ethernet became popular, now they took that physical layer of the FDDI and adopted as a standard for what? For the Ethernet. Which is better, easier. Okay. How this ML3 works? ML3 has 3 levels, like V plus, V minus, and 0. Let's say this is like 1 volt, this is minus 1 volt, this is 0 volt. Okay? And this is the state diagram for that. If you are in the state, you have 2 states for 0. One is 0 when you come from the positive voltage. One is the 0 when you come from negative voltage. And that's the memory of the system. It works like, if I am in here, for example, if I have 0, I stay at the same level. If I have a 1, I go to the next level. After 0 plus, next level is minus. If I am in here, I receive a 0, I stay. If I have 1, I go to next state. Okay? So, and so on and so forth. Okay? So, what I'm going to get is something like this. Okay? If I have 1, for example, and I was in the 0, 1 comes, I was in the 0 state before. Okay? This 0 state actually before. Now, I was in this 0 state before. 1 comes. When 1 comes, I go to what? Minus 1. Minus V. Or minus 1 volt. Whatever you want to call it. Next bit is 0. I stay in the same place. Next bit is 0. I stay the same. Next bit is 1. I come from here to what? To minus V. Minus V is this one. 0 level. Okay. Next bit is what? Next bit is 1 again. When it's 1, I change the state, go to here, which is positive voltage. Another 1 comes. I go to the next stage, which is 0 volt. Another 1 comes. I come to what? Negative volt. 0 comes, I stay, zeros. 1 comes, I go up. 0 comes, I stay. 1 comes, I go up. And if I'm at top, 1 comes, I go down. So either I'm going with 1s, either I'm going up the steps, or I'm going down the steps. Okay? And this is what the coding is. Now, with this coding, I can go this bandwidth, if it is like 100 megabaud, it works. Okay? I can accommodate what? 125. The bandwidth of this is less than 100 megahertz. Because I went from binary to what? To trinary. Okay? If I wanted to send these bits, they needed 125 megahertz bandwidth. I went to the trinary, I brought it down within the 100. Okay, so I can send it over those bandwidths that I have. Okay, yeah.
We did that multiple things. Before this coding, we had two transitions. We made sure that we had two transitions to ensure synchronization.
Yes.
Right? These are the ones and zeros currently placed here are also in the order like 5 of them. Each grouping of 5 has two.
Yeah.
So in case we note the second grouping, we see that although there are two transitions, there is a long stretch for which the signal is at the same, like.
Which one?
In the second.
Oh, you mean that the codes in here, you think that is not 4B, 5B?
No, they are.
They are 4B, 5B.
They are
because
4B.
At least they have two ones.
Yeah, they have at least two.
Yes.
In the second dip that we have, from the crest to the dip, there are initially two transitions, one after the other, and then there is a whole blank for like 1, 2, 3, 4, 5 bits.
Yes.
So what I'm saying is those two transitions could be spread over a longer distance as long as 5 bits. What is the minimum quanta for which like you should have transitions in which you do not have like synchronization problems?
You mean that you say that this is stream?
The stream is still like a pretty long time where they can.
All of these things, the way that they do it experimentally really. Okay, they do it experimentally. They send a big stream of data. Okay, and they will see what will happen. But theoretically, what is the maximum that they can happen? For every 5, at least you have 2. Okay, so you may have like 2 1s and 3 zeros, and after that, 3 zeros, 2 1. So maximum is 6. Maximum would be 6. Okay. If they have a code, you have to check the table. I mean, you can find out from the table. If they have all zeros and then 1 1. Okay. But what you see in here is one of the longest that you can see. Okay. That is true. Okay. So this is ML3 and 4B, 5B. What is the story of the other coding? Remember that. Those two were related to what? Related to, 4B, 5B and ML3 were related to FTDI. FTDI Ethernet, if you want to call it. Now, if you go for the other one, which is using twisted pair. Now you have 4 pair of twisted pairs. Okay. And this 4 pair of twisted pair is shared between 100 VG LAN and fast Ethernet. Okay. Both of them have 4 pair. In 100 VG LAN, all of them are the same. But again, Ethernet version is strange. The wiring is strange. Okay. The wiring that they have actually, let me first show you the wiring, is something like this. This is not something like this. Is the wiring. Okay. Very strange. See, there are 4 pair of wires, 2 of them, and you have then 3 pairs of transmitter receivers. 2 pairs of the transmitter receivers are connected with 2 pairs. The other ones are separated. This is like full duplex. These are half duplex. Very strange wiring. 100 VG LAN is the same for all of them. It has 4, 4. Okay? In here they have made this strange wiring. Okay? So, you have 4 pair of wires, but actually you are connecting 3 transmitter to 3 receivers. Is that right? 3 transmitter to 3 receivers. Okay. If you are very smart, you can use this as like independent full duplex, and the others as like half duplex. But nobody does that, really, because they usually take the whole thing as ones. But anyways, I have 4 pair of wires equivalent to what? 3 lines really. Is that right? if I have 3 lines and I have 100 megabit per second, each of these lines should carry how much? 33 and 1/3. Okay. Now, if I come to like each of these wires, these are Cat3. These are not Cat5. What was the bandwidth of Cat3? Was like 16. If I go to trinary, which I go to trinary because my coding goes to trinary, okay, 16 gets to what? Something around 25. So the baud transmission, symbol transmission in here is what? Is what? 25 megabaud. Symbol transmission rate is 25 megabaud. But what do I do in that? Means that I have 25 mega transmission per second. I mean trinary transmission. Okay? Now, but the coding that I have does every 8 bit gets encoded to how much? 6 transmission. Is that right? 6 trinary transmission. As a result, my data rate for each of them is what? 8/6 of this thing, which is 33.13 megabit per second. Did you follow that? So, on the wire, I'm sending trinary signal at the rate of 25 mega trinary or transition per second. Okay? But each 6 transition is really 8 bits. So if I want to go to the bits, this is 33.13. And 3 of them is what? 100 megabit per second. Understood? So now I can go back to my earlier thing. So the way that it looks from the user point of view, regardless of the fact that I have 4 sets of wiring, actually I have 3 lines to communicate. Each of these lines are carrying 25 megabaud. Means trinary per second. And they are transmitting what? The 6T part. 6 transmission part. What comes in is 8-bit at the rate of 100 megabit per second. So the data which is coming at the rate of 100 megabit per second, I get every 8-bit, I translate to 6 transition. Okay? And I send it at trinary, which is equivalent to 33.3 megabit per second. And 3 of them is 100 megabit per second. Understood? So this is how the coding works. How you get the 100 megabit per second with 4 wires, which are really, I mean, logically they are 3 wires. There are 4 wires which are logically 3 wires. Okay? And they are sending what? 3 levels rather than 2 levels. So they are sending at 25 megabaud at 3 level, which is equivalent to 33.3 at the binary level. Okay? And 3 of them forms the 100. So what is that coding? This is a part of the table for that coding. Do you remember that in the X series, you were first doing 4B, 5B, then to trinary? In here, you do that directly. You get 8 bits, which now they are in the octet in here. Means that this is 0, 0, 0, 0, 0, 0, 0, 0, 0, on 8 bits. You map that to what? Plus, minus, 0, 0, plus, minus. Okay? And then the next one, 0, 1 is this thing. So the way that you're doing the mapping in here really is just direct to 3 levels from 6. From 8 to the 6 level. This is a part of that map. Of 8 bits to 6 bits. Okay, from 8 bits to 6 transitions, sorry. 6 tri-level. And this is how this one works. Okay? It's interesting and confusing, isn't it? So in the summary, I have 2 options for the X. One is this option, we have 2 pair of wires, and these 2 pairs are carrying their own data rate, the way we described. The other one, I have 4 pairs of wires, which are reduced to 3 pairs, logically, and the tricks associated to that. These are what? The 4 standards, the 3 standards that I was talking about. Okay? Which are these. That's the whole chart now. You know the transmission in all of them. Now, when they were going from 10 megabit per second to 100 megabit per second, this is the main part, the physical layer that they did. They were inspired with what? With FDDI originally. And then they wanted to go to Cat3. And they did this innovation of 4 pair. Okay? That's the main part. But at the same time, since they were doing a new standard, they started to take the communication between the terminals into consideration. Because now I have a network that may have a bunch of 10 megabit per second, a bunch of 100 megabit per second. Okay? And they may have different version of that 100 megabit per second. So they try to add to their lower layers another layers that they call it auto-negotiation. Auto-negotiation, what it does is that with the auto-negotiation, you're going to find out that which of these protocols are used by checking the channel, not even by communicating. By checking the channel, the voltage levels, etc., you can find out what you're using. Okay. The second thing that you can use, in addition to that, this is like, if you have in my laptop, for example, there is light in there on my 100 megabit per second, which whenever it is 10 megabit per second, it's on. And whenever it's 100 megabit, it shows another indicator. That's auto-negotiation. Okay? Which recognizes what is the data rate and turns on the light. And I know that what is the data rate that I'm on. Okay? That's one advantage. But while they were doing that, they added some extra feature. One is the so-called next page feature. That's a general mechanism that 2 terminals can talk with one another. 2 NICs can talk with one another and send more information back and forth, which is related to that particular manufacturer. Okay. Then they have another thing which they call it remote fault indication. This is another layer of signaling that detects the fault conditions. In data communication, we are very sensitive to fault conditions. Okay? And wherever we can add something. As you increase the data rates, these things become more and more physical layer dependent. Okay? And you want to detect more at the physical layer. And that's what they are doing in there. Okay? So this is one new features that they have, that they call it what? Auto-negotiation. In addition to that, they have generated, now that auto-negotiation, for example, is a clause for itself. Okay? FX is another clause. Okay? That's, I don't know, auto-negotiation is clause number 28, I believe. And then the other one is clause number 22, etc., etc. There are a bunch of 7, 8 clauses on top of the existing 20-something that they went to the fast Ethernet. Now, another clause in there is classes of repeaters. They define 2 classes of repeaters. One are the repeaters that collision domain is only in one repeater. The other one is the one that collision domain can be shared between 2 repeaters. That's like another format in there of those clauses. So generally, collision domain is the number of terminals who share the same collision with one another. Okay. and this is class 1. If you have class 1, you have one class 1 repeater. Only these terminals share the collision domain. If you have class 2, you connect one of them to the other one, and all of these guys share the collision. Using these features, you have some flexibility in putting together your system. Okay. The next issue is the issue of virtual LAN. And I will just tell you what it is, and we come back in the next lecture to pick it up. Okay. VLAN protocol permits adding a tag so that you can have virtual local area networks. Who wants to use virtual local area networks? I mean, I'm sitting at my home, on my Ethernet at home, and I want to connect it to Ethernet in WPI. Okay? That's the VLAN connection. Okay, I want to be a part of the LAN in WPI while I'm sitting at home. In order to do that, I have to add a sort of tag to tell people that I belong to this thing. Okay, that tag is called virtual local area networks, that tagging. How to implement it and how it works. Okay, that we will discuss in next lecture.